thin star, you need to be closer. The hot star and bright need to be farther away.
Scientists have calculated just how many rocky planets may lie within the Goldilocks zone of their stars. It comes out to over 30 billion potentially watery worlds. Even more remarkably, recent discoveries have shown us it's not just planets that can pass one of the Goldilocks zone. There may be moons, most of the planets we're finding are big Jupiter-sized planets. However, a lot of them are orbiting roughly where the Earth is orbiting the Sun. The planet we're finding can't support life. It could have a moon with an atmosphere that could support life. The biggest of these rocky moons may resemble our home.
There could be billions upon billions of exomoons out there, and even perhaps countless paradises teeming with life.
David Gibbing searches for exomoons by looking for double dips in the brightness of distant stars.
We look for exomoons in a very similar way to the way that we look for planets. We're looking for the transit of our host star. Now, if that planet had a moon, then we should expect to have one big dip due to the planet, and then one smaller dip either to the left or to the right due to the moon.
Habitable exomoons may play host to one of the most spectacular sights in the universe. Imagine a warm, rocky world just like ours, with oceans, mountains. Out of the sky, a massive ringed planet with a fiery sister moon shooting hot magma into space. Exoplanets, and now the vast potential of exomoons, hint at a galaxy filled with the possibilities for life. But a rocky surface and liquid oceans may not be enough. Biology needs the breath of life, air.
全部ちゃう。あんな鳥見たな。不思議だな。
Backlit by the sun, a halo appears around the Earth. A pale blue ring of light, our atmosphere. And we owe it everything. The Earth's atmosphere provides the gases that fuel the biochemistry of advanced life. But it also protects the oceans from the full fury of the sun's rays, preventing the water from boiling away into space. Without an atmosphere, there would be no wind, no rain, no fresh water, probably no life. Atmospheres are absolutely essential for life. Take a look at the planet Earth, and you realize that just like the skin of the apple, the skin of the apple preserves the apple. Well, the atmosphere of our planet preserves the oceans and makes possible the presence of life as we know it. Scientists in search of living exoplanets hope to detect the thin, gassy envelope that should surround these alien worlds. To do it, they're turning to the power of rainbows. In the same way that water splits sunlight into a rainbow, astronomers use instruments to split starlight into a band of colors called a spectrum. It's one of the oldest tricks in science, and one of the most revealing.
Several hundred years ago, scientists first began to take something like a prism and put it in front of their telescope. So they started taking the light from stars like the sun and actually spreading it out into a spectrum. And what they saw was kind of surprising. So instead of seeing a continuous rainbow of light, they saw that rainbow, they saw these dark lines superimposed on top.
Each chemical element in the star's atmosphere
Sì, tornare
absorbs different parts of the spectrum, creating signature dark bands.
For instance, up the top, there's other lines in the yellow part of the spectrum, which are due to sodium.
Like a DNA profile for stars, spectral analysis has taught us almost everything we know about stars today. But these same lines may hide a marvelous secret. The faint signal of alien atmospheres. And perhaps also alien life.
The challenge is that
have their own faint lines on the star's spectrum.
So as we watch the light from the star transmitted through that atmosphere, its atmosphere is going to act like a little filter. So part of the starlight is going to pass through that atmosphere, imprinting extra lines on it, which are due to the planet's atmosphere. So that change in the spectrum tells us something about the properties of the planet's atmosphere.
The one chemical astronomers most want to find is oxygen, because only life can produce enough oxygen to be easily detected. So-called biosignature. The race is now on. Find biosignatures in the atmospheres of rocky exoplanets. And while some groups look for rainbows indirectly, others are tackling the challenge head-on. Alright, we're off. Ben Oppenheimer is part of a team trying to take direct photographs of exoplanets using massive ground-based telescopes. We're within minutes of taking our first long exposure, and I hope it's good. The greatest challenge to imaging exoplanets is the blinding light of the parent star, which shines tens of millions of times brighter than the planet itself. The trick is to stop the light of the star from entering the telescope's sensors by blocking it, using a series of masks and lenses called a coronagraph.
Right now we're standing right underneath the telescope's primary mirror. The light comes through a hole in the middle of the mirror and goes into this crazy box here, which is full of optics, motors, sensors, and electronics that all allow us to precisely control the starlight that's coming through the system.
Using state-of-the-art software, they manipulate the coronagraph to black out the unwanted light. Under good conditions, we can actually carve dark holes into this image of the star so that we can see really faint things in those regions. Coronagraphs present an intriguing problem, though. Errors within the optics produce tiny flares of starlight called speckles that look just like exoplanets. But man has come up with an ingenious way to tell speckles from planets. So we've developed a technique where we exploit an aspect of speckles, which is that they change position in the image depending on what color you take your image at. So Ben takes the same image of the star through different color filters and runs them like a movie. The speckles appear to move across the screen, but the planets stay stock still, allowing Ben to easily pick them out. And so I'd like to point out that there is a little thing right here that if you watch, if you're careful, you'll notice that it doesn't move, and the speckles are washing over it. This stationary blob is a candidate exoplanet. And below it, and to the left, is a second. They both appear to orbit a star around 200 light years from the Earth. Just a decade ago, capturing an image like this through a telescope was unthinkable. But today, thanks to the ingenuity of astronomers like Ben, we have hundreds. And by analyzing the light from these distant worlds, scientists can work out their chemical composition and potentially the fingerprints of life. At this point, we're studying much larger planets, gaseous things like Jupiter, that most likely don't have any kind of life like we know it. But that's a first step, and we're going to fainter and smaller planets as time goes on, as we develop this technology. In the not-too-distant future, scientists may be able to simply scan a star for Earth-like planets and find the signature of life there. We can look right at the light from a little planet around its distant star, and that opens up a whole range of possibilities for us to not just detect the planet, but to study the planet.
I mean, this all sounds like science fiction, but there is a reality to this. We have a scientific method to actually determine whether there is life on another planet.
Life is one thing. Intelligent life, another altogether. That requires billions of years and a powerful force field like the one we owe our lives to every day. If an alien astronomer were to file a report on our own solar system, it would be a surprising observation. Because of all the 8 planets that orbit the sun, they could easily conclude